Okay, so let's start. Yeah, thank you everyone for coming here today. So as a brief overview, so the point of this course is to try to introduce some ideas in condensed matter physics, which actually turn out to use a lot of the same techniques and constructions that are used in particle physics. So to begin, okay, so today I'm going to talk about mean field theory. Okay, so mean field theory is a common technique that appears in many, it has many condensed matter applications. And for the purpose of this, I will talk about magnetism in solids, in particular, the transition between paramagnetism and ferromagnetism. Okay, so, sorry, maybe just move this. Okay, so in general, the magnetic field can be written in two parts. So in SI units, there's a mu0, and then so this B can be decomposed into an H and an M. And here H is the macroscopic magnetic field. Or if you like, the effective field in any medium. So in vacuum, V is just constant times H. And M, which will be our main focus today, is the magnetization. Or the magnetic moment per unit volume. And so in solids, spins of atoms can interact. And they can largely interact in two ways. So one way is that they can interact with an external field. Which is the case in, for example, paramagnetism.
By the way, what do you mean by spin? Do you mean the spin of an electron or the
It depends. In practice, electrons, or what I'll talk about. And they can interact with an external field, or they can interact also with each other. And this is the case in ferromagnetism. Of course, there can be all kinds of interactions in general, but what we're concerned about is what interactions dominate in any given situation. So first, let me review some facts about paramagnetism. So paramagnetism is something that happens when you have a solid that has free electrons, which should be unpaired or they're not paired up. So consider a solid with unpaired electrons. So we have some solid, and it has some electrons around the place, and each electron will have a magnetic moment, mu. And then we want to apply an external magnetic field which we can align along any direction of our choice. And here I'll put it along the z direction. So now, if we compute the to study the situation, first we need to know the magnetic moment of these unpaired electron spins. And in particular, since the interaction is given by minus mu dot b, this is what gives the energy, the relevant component will be the z components of the magnetic moment. And this is given by minus, because the electric charge is negative, some g factor times the Bohr magneton times the spin of the electron, the spin eigenvalue in the z direction, where, mu b is just EH bar over 2 electron mass. And the g factor is roughly 2. And of course, the spin in the z direction can be plus or minus 1/2. So if we put all this together, we get that the magnetic moment is, so since SC is plus or minus 1/2, and this is by 2, the minus sign there makes this minus or plus mu b. And now let's compute the magnetic energy of this. So is it okay to erase this part? So the magnetic energy as I mentioned over there is minus mu dot B, which in this case is just plus or minus mu z B. So with this information, we can calculate the average magnetization over the lattice. So first of all, let's compute the average magnetic moment along the z direction. So we can do this via Boltzmann statistics. So it's the sum over every magnetic moment, or is the sum over every state that this magnetic moment can be in, which I'll label by I, times the Boltzmann factor e minus beta ei, divided by the partition function. So this works out to be, so for spin plus a half, we have minus mu b. So we have minus mu b, and then the energy is plus, sorry, this should be mu b. Yeah, the energy is plus mu b b. So minus beta that is minus mu b b over Boltzmann's constant times T, temperature. And then the same thing with the opposite sign. So we have plus mu b e to the plus mu b b over mu b T. And then the partition function is this without the mu b's and the sign. So it's just the sum over probabilities, which is e to the minus mu b e over kb t plus e to the plus mu b e over kb t. So this is just mu b times hyperbolic tangent of mu b b over kb t. And then so then this is the average magnetic moment per electron spin. But so if we have n of them per unit volume, the induced magnetization so m is just n times this, the average of mu z, which is some ms times and this hyperbolic tangent. Where ms is N times mu V is the saturation magnetization. So what we essentially find here is that when we turn on this external magnetic field, we induce a magnetic moment. We induce a magnetization in this solid. So if we plot the magnetization, maybe normalized by ms, against this argument mu v e over kbt, this is a hyperbolic tangent function. And the magnetic susceptibility chi is defined via the relation m is chi h for linear weak field materials, which in this case is approximately chi over mu 0 b. So for the weak field regime, we are somewhere around here. So this is approximately linear. So m is roughly ms mu v b over kbt. Which means that the susceptibility is, so plugging in the definition of ms, this is, and including this mu 0, it's n mu 0 mu v squared over kbt. And in particular, it's proportional to 1 over t, and this is known as Curie's law. Which is named after Pierre Curie, not Marie Curie.
So how is the estimation value of the chi? Because we said the m is proportional to h, where the coefficient is chi. So if you want to assume that the h field is approximated by the b field, then we should set chi as a small value. So I want to ask that is chi small?
Yeah, this should be small. So this is valid in the limit where, yeah, this is much less than 1.
How do we know that the chi in this equation is small?
I mean, we are considering. I guess it can be checked, of course. So yeah, there is some regime where this is valid, and of course it may depend on the material, but so in particular, there's a subset of materials called linear materials where this is valid. And in those cases, we can use this approximation. Any other questions so far? Okay, if not, then I'll go on to the second kind, which is ferromagnetism. So in a ferromagnet, we have the following situation. So at some high temperature, we have some lattice of atoms. And again, each atom will have some unpaired electrons associated with it. And there will be a net spin per lattice site. So in the case where in the case where the temperature is above some critical temperature, then all of these will be aligned randomly. But in the case where, let me just quickly do this again. In the case where the temperature goes below some critical value, then all the spins will tend to align. So ferromagnets spontaneously magnetize. Below a critical temperature. Tc, which is also known as the Curie temperature. And they do this even in the absence of an external magnetic field. So for example, if we consider iron, this has a Curie temperature of around 10 to the 3 Kelvin. And in particular, the prefix ferro comes from iron in Latin. So obviously this was known for a long time, but nowadays we understand the microscopic origin of ferromagnetism. And it comes from a Heisenberg-style exchange interaction. Which is present between unpaired electrons. And basically, the interaction for the exchange Hamiltonian is of the general form, some minus, so that it's energetically favorable, and then a sum over I and j of some coefficient, usually called jij, times then the interaction si by sj. And in ferromagnetism, jij should be non-zero and positive for nearest neighbors. So to proceed, one useful model of ferromagnetism is known as the Weiss model.
By the way, should J be 0 for non-nearest neighbor?
Let's say yes. Yeah. Of course, in general, you can have all sorts of interactions, but as a good approximation, in many situations, we can consider only the nearest neighbor interactions. So in the Weiss model, we define a molecular field at, say, the I site as Bm I as minus 2 over G mu B times the sum over J of Jij Sj. So essentially, it's for a given electron, the ith electron, this is some kind of effective magnetic field that it experiences due to the spins of all the other electrons in principle, all the other electrons in the solid. Although in practice, we may just consider nearest neighbors to leading order. So then with this definition, then our exchange Hamiltonian looks like G mu B sum over I Si inner product with Bi M. And the factor of 2 has disappeared because this original sum double counts interactions.
Is B a real magnetic field or an effective field?
It's an effective field. It's not a real magnetic field.
So it is originally due to the spin-spin interaction, right? Not the magnetic one.
Right. It comes only from the spins interacting with each other. So then if we apply an external field, B, then the Hamiltonian will be the exchange interaction plus the external one, which is minus mu dot B, which is G mu B, or the sum over all the sides of mu dot B, which is summa I SI dot B.
I don't understand it factor two.
It's because this was the sum over all I and all J.
Yeah.
So you have, for example, S1 dot S2, and then you also have S2 dot S1, which is the same
But
thing.
below you have again, if you sum over I, you don't see anything. You got same sum as above.
I think that the energy is proportional to the number of couples.
Yeah.
And the number of couples is n minus 1 divided by 2, that for larger n is n squared. No. There should be a factorial or some. The number of couples, right? Should be n squared divided by something like n squared divided by 2.
Yeah.
But I think if we consider a near neighbor interaction, then the remote interaction should be proportional to n. N. I mean, yeah, the number, not x squared. But
Probably it's okay because if you sum over I and j, you get n squared. And
So if above definition is pairwise sum, then factor two should be.
I mean, you reduce the energy by amount to minus S1 S I S J for each couple. So you don't do that twice.
Then the factor two should be in the 1/2 rather than 2. It should be half.
Yeah, so there should be a factor of 1/2 there. Probably in the Hamiltonian.
Rather than 2, it should be 1/2. Right? Yes.
All right. So yeah, okay. So I kind of glossed over this, but so what I recall is
That is pairwise sum, you say.
so I think if this could be written as, say, sum over I greater than J 2 times this thing. And then you take this factor of 2 into this definition. So maybe this is, I think to correct it, this should be a sum over some J less than.
Let's move on.
Yeah.
Yeah, it's just
Yeah.
Yeah.
Okay, so anyway, this Hamiltonian can now be written as G mu B times the sum over I SI dot B plus BM I. And then we assume that we're just
That's a very stupid question. So I understand that the Hamiltonian is a spin exchange interaction, but at the fundamental level, I mean, we have just electromagnetism, right? What is the coupling? So how do you explain this coupling at the?
Is it after integrating a photon?
so you have to
So
how to explain this.
yeah, there is from first principles is possible because this is an effective Hamiltonian.
So I kind of skipped over that due to time, but you can explain it basically by considering the Pauli exclusion principle for the electron wave functions. So your electron state, say for 2 electrons, has some spatial part, and also a spin part. Yeah. So since they cannot occupy the same state, then you will have you will have either this is antisymmetric, this is symmetric, or this is symmetric, this is antisymmetric. And then and then when you plug in the spin part, it basically evaluates to this form. And there's I think actually it comes back to the factor of 2. Maybe I need to check, but because you have a difference of so you'll have a kind of the antisymmetric part of this will be a singlet, and then the symmetric part will be a triplet, and there will be a singlet triplet splitting. And that energy difference is what gives rise to this interaction. Okay. So then to make progress, we want to assume that this molecular field, this effective construction, is somehow it should be proportional to the magnetization of the, or it should be proportional to the average magnetic moment in the solid. So we assume that the phi is some constant lambda times m for all I. So we assume that it's all very uniform, very homogeneous, and every electron feels the same molecular field. And then the same as before, if we consider some magnetic fields in the z direction, then also we expect the induced magnetization to be in the z direction. And then we just perform the same calculation with this, with these 2 components. And we find that the magnetization is ms hyperbolic tangent of mu b now times B plus lambda M for KBT. So then if we consider the case where the external field B is 0, and then we want to solve this.
What was it? MS?
MS was just the it's just a constant. It's the number density times the times mu B.
No.
So now the situation for B equals 0 looks like this. So if we plot M over MS up here, and now on the y-axis, or sorry, the x-axis, we have mu B lambda M for KBT.
This is kind of weird because the x-axis and the y-axis both have M. So
Yeah, so but again, we have this kind of behavior. So something like this is this functional dependence. I mean, if you like, we can call this some variable y, and then this is y here. And then we want to consider various cases where y is also proportional to m.
So this relation M is approximately MC doesn't, so when B is 0, there is no preferential direction. So I don't understand. So it's not, when B is equal to 0, there should be no, right? No, all directions are equivalent. So I don't, probably it's not valid in the case of B equal to 0.
So I guess this you can understand as a situation where, so in a ferromagnet, if you turn on a magnetic field, then even if it was magnetized in some direction, the magnetization will switch to be parallel to the magnetic field. And then if you,
you mean this is okay, this is memory. So first you switch it on and then you switch it off.
Right. So
And so this is a domain. This is inside a domain, a particular domain of the ferromagnet.
right. Yeah.
In other words, in every domain, the z direction will be different.
Right. In general, that will be the case. But if you turn on a magnetic field, then every domain will point in.
Yes.
Yeah.
In principle, yes.
Yeah.
System has memory. It has been so you broke the symmetry before.
Yeah.
And then you set B equal to 0, and there is a hysteresis.
Right. So okay, so I'm just going to call this Y. This may be better. And then we want to, so this equation for B equals 0, it's self-consistent, or we have a solution for the effective magnetism when so
Still, I'm confused because the Y contains the temperature, right?
yeah.
So we know that when we increase the temperature, eventually the magnetization is gone.
Right. So basically, yeah, this is
Which is exactly, it's going to 0. Yeah.
right. So
okay. 0 means that it's average, you average to 0 everything.
Yeah, and this is all in the absence of a magnetic field. So you know, if you like, we turn on a magnetic field to get everything aligned, and then we turn it off, and we see the behavior. So we can consider different cases. So first of all, if t is greater than tc, so t is large, it means then this can be thought of as m as a function of y. This will be very steep for a large t. So we would have something like this. And then the solution is given by anywhere that this intersects this. Anywhere that these two curves intersect gives the solution.
You mean the determination of TC? This is what you mean? No, I didn't.
Maybe I need to just a second. I think I need to refer to it once.
TC is something Y and derivative Y.
Yeah, so I forgot to define TC. Let me do that. So the statement is that when b equals 0, solutions with non-zero m are possible for t less than some tc, which is mu b lambda m s over kb. Yeah, which you can just also write as n lambda b squared. Okay. So, right, so then if we then, yeah, so we can rearrange this into m over ms. Is ABT y over mu b lambda m's. So then the solutions are given by the points where this line and this line intersect in this graph. So for t equals tc, for t bigger than tc, these intersect only at n equals 0. But for t less than tc, then there are 3 intersection points. So then we can have a solution which turns out to be a minimum. With non-zero magnetization. And then just one more thing to say about this, which is if we then turn on the magnetic field again, so non-zero magnetic field, and if we're above the critical temperature, then and again we're in the weak field linear regime, we can compute from m over ms in that limit. So the tangent function is approximately 1, or is approximately just its argument. So, and then using the definition of TC, we can say this is TC over lambda ms B plus lambda M over T. And if you stare at this enough, then you can see that the susceptibility is again approximately mu naught M over B. And this is proportional to 1 over T minus Tc, which is known as the Curie-Weiss law. Okay, this concludes the kind of background review of magnetism. So are there any questions so far? Okay, I don't see any questions, so let's continue. So the details here are not so important. It's just to give you a feel for what for some basic models of magnetism and some explanations for these phenomena. So with that, I want to move on to the main point of this lecture, which is Landau mean field theory. Right, so as we've seen, microscopic descriptions of magnetism and also other phenomena, they can be, it turns out they can be very complicated and very material dependent. So the philosophy of mean field theory is that we want to take a phenomenological approach, a general framework that we can apply to various situations. And in particular, it's a coarse-grained framework. And we can use this to describe critical behavior and phase transitions in many different systems. So it's a phenomenological and coarse-grained description of critical behavior in many systems. In particular, this often applies in many body systems. So maybe I'll say that actually. And many body systems. So they always feature an order parameter which, to make contact with this magnetism discussion, I will call M, and it could be a function of some coordinate x. And this order parameter is used to, or it characterizes the system near a phase transition. And it's usually equal to 0 above some critical temperature and not equal to 0 below some critical temperature. And in general, we can consider this M to have capital D components. So it's some RD variable or function. And then for the coordinates, we can also consider various situations corresponding to the, sorry, let me just make these upper indices, x1 up to x little d, which is the spatial dimension of your system. And this is a general framework, so it applies not just to magnetism, but to a wider range of situations as well. And some examples of that are the following. So for capital D equals 3, this would correspond to isotropic magnets. Very simple. But we can also have D equals 2. And this will be the case in, for example, superfluids and superconductors. And also planar magnets. So magnets where the magnetization is confined to a plane. And then also even in D equals 1, this can represent liquid gas transitions. And of course, uniaxial magnets.
What is M? What is liquid gas transition?
Yeah, I'm not sure off the top of my head. I need to look at it. And so, yeah, you usually in many situations, the spatial dimension will be 3, but sometimes D equals 2 can be if we have something that's defined on a film or a surface. or d equals 1, for example, on a wire. And then for lattice spacing, which I'll call little a. Maybe I should put something on it. One important point is we want to assume that the relevant degrees of freedom describing collective phenomena which are associated with long-range order that since these are, so having long-range order means we have, for example, all the magnetic moments being aligned over a large scale. So we assume that the degrees of freedom describing that have wavelengths that are much bigger than this lattice spacing. And this is maybe the first contact with particle physics ideas, because we can think of this as an ultraviolet cutoff of the theory. So what do we do practically? So in practice, we expand the free energy density little f as a power series in the order parameter while respecting the symmetries. So any symmetries of the system. For example, rotations. So for this, we can write f of m is some constant piece, f0, and then the next contribution is then proportional to m squared, and can put some t over 2 times m squared. And then the next contribution is quartic, so that would be m to the 4, and so on. And
It's pure scale, yeah? Inner product scale.
no, it's this is m dot m.
Yeah, but the quartic
Quartic is
pure.
Square root of
I see, yeah. Sure.
Okay, talk about symmetries. If you are in a lattice, you have discrete symmetry.
So this comes back to the point that we want to coarse grain over it. So ultimately what we want to do is take a continuum limit of the theory.
So you only care about size much larger than 80.
Yeah.
So we don't have a cubic one, right? Because of the symmetry.
Right. Yeah, we want to. So for this, at least for this part, we want to respect rotational invariance. But of course, if we can extend it to also include an applied magnetic field, and then we'll have something like if we have some applied magnetic field, there can be terms like mu0 h dot m, which comes from h dot b. So note that this, if this is non-zero, it breaks rotational invariance.
For d equal 1, you can have something.
If you want to, sorry, say again.
For d equal 1, so like well, the dot product doesn't mean it's no longer a dot product, right?
Right.
It's gonna have a linear terms.
True. Yeah. 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 So, yeah, maybe we'll say part 2. Okay. Okay, and then we want to find a configuration that that minimizes the free energy with respect to this order parameter. So a simple case would be that this m of x is just to the leading order. The background is just some universal m, and it's aligned along the unit vector parallel to h. So if we consider that case, and then we minimize f, then say that 0 is df by dm, would then be tm plus u m cubed, 4. I'll just keep these terms, and there can be a minus mu0 h. So then for h equals 0, then this reduces to m times t plus 4u m squared equals 0, which means there are two solutions. M can be 0, or m can be plus or minus square root of minus t over 4u. Okay, so this is very general, but now let's think about the case of ferromagnetism. Near its critical temperature. In this case, we can identify this little t as a kind of reduced temperature. So it's T minus Tc over Tc. If we make this identification, then we see that for T greater than Tc, there's only one real solution.
So where is the temperature and your free energy? There's no.
So this T here, I'm identifying as T minus Tc over Tc. Yeah, this one here.
Why that should be the temperature?
So basically, this is a phenomenological model. So a priori, we don't know what these parameters are. And then we solve it, and then we compare with real systems to then identify these parameters. So in principle, they can depend on temperature or pressure or any other variables of the system.
So the idea is that above the critical temperature, the minimum of the energy is for m equal to 0.
Yeah.
And below the critical temperature, you use a new solution different from 0 appears.
Right.
In other words, you can just solve that equation as a function of t, and then you decide this is the identification. So
Right. Exactly.
So maybe if you do a graph, maybe you can help, right?
Yeah, I'm about to do that.
Yeah.
So yeah, for T greater than Tc, there is a minimum at m equals 0, and for T less than Tc, there's a minimum at some other m, which is proportional to Tc minus T to the 1/2. So basically, f of m as a function of m looks something like this. So if we consider first T greater than Tc, we have only this one minimum here. And then for T less than Tc, we have this configuration, and either two minima.
This Tc should be expressed in terms of U.
Yeah, you should
have this T and U, it's nothing else.
Yeah, so you have this U, which so in general you can write, T as something plus some order T minus Tc squared, and similarly U. Yeah, it turns out you can just write this as some constant plus something of order T minus Tc. So this is only a good description close to the critical temperature, or at least that's the idea. So it's a phenomenological description that, in general, as this becomes large, then you can have higher corrections. Yeah.
So the temperature dependence of T and U, no, T is fixed basically. U is approximately constant, close to the critical temperature.
Yeah. So yeah, so this is something that people identify phenomenologically.
I think that the time is over. There is another event at 4:30.
Yeah, I have. If you'll allow me to write down 2.5 more lines, I can finish this all off. So just to mention one final thing, which is critical exponents. So near the critical temperature, in general, we can say that, for example, we can define various critical exponents, and basically it's the dependence of various parameters in our theory on T minus Tc, or on each other. So usually m order parameter is Tc minus T to the beta, and the susceptibility is T minus Tc to the minus gamma, and m is proportional to h to the 1 over delta. And yeah, as we can see here, beta is, in this case, beta is 1/2. Gamma is, well, we can compute it in this scenario as well. But it's basically gamma is 1 from the Curie-Weiss law, which we also recover in this case. And yeah, delta turns out to be 3, which we can see from this equation corresponding to the minimum when T equals 0. So at the critical temperature, then m cubed is proportional to h. Okay, yeah, I think that's a good place to stop. And next time we'll go beyond mean field